Hello there and welcome. The world outside can be busy and loud, but here things slow down. Tonight we are not looking at mountains or rivers or the night sky. We are slipping into a hidden realm where a single photon can travel like a wave yet act like a particle, where atoms can communicate across the vastness of space and even the emptiest vacuum bubbles with energy. We will travel gently through quantum fields, teleporting particles, and moments when the act of perceiving changes what exists. This strange shift from the predictable to the probabilistic is why quantum physics feels like a different universe, hiding within our own. It is not that the everyday rules break, it is that they were never the whole story. Beneath them lies a stranger, softer framework that holds everything together in ways we are only beginning to understand. Most of us will never directly see the quantum world. Its smallest building blocks are far tinier than the wavelength of visible light, so they remain forever hidden from our eyes. Yet their behavior shapes everything we touch, breathe, and become. In this unseen realm, particles drift like ripples in a pond, pop into existence for fleeting moments, and sometimes act as though they are in several places at once. The rules here are written in mathematics so unusual that even seasoned physicists often admit they use the equations without claiming to fully grasp their meaning. This is not just a smaller version of our reality. It is a fundamentally different one, operating on principles that defy our common sense. And yet without this invisible world quietly playing out its patterns, the visible universe, including us, could not exist. Fact 1. Energy is not continuous. It comes in tiny packets. In the late 1800s, scientists thought energy was smooth like water flowing from a tap. Then came the shock. Under certain conditions, it is not smooth at all. Light, heat, and other forms of energy are made of tiny, indivisible quanta. A quantum is the smallest amount of energy a system can gain or lose, like the smallest coin in the currency of the universe. This discovery, sparked by studies of how light interacts with matter, overturned centuries of physics. It explained why heated objects glow in the colors they do, why atoms absorb and release light in narrow bands, and why energy can sometimes feel like it appears in discrete jumps instead of steady flows. Without this idea known as quantization, modern technology from lasers to computers would not exist, and the doorway to quantum theory might never have been opened. The realization that energy arrives in pieces rather than flowing smoothly changed how we see the structure of light itself and laid the foundation for understanding atoms, molecules, and everything built from them. Fact 2. Matter can flow like a wave yet strike like a particle. It sounds impossible. How can something be both a wave and a particle? But that is exactly how quantum objects behave. Shine, light through two narrow slits, and it spreads into rippling interference patterns, a hallmark of waves. But detect the light particle by particle, and each one lands at a single point like a tiny bullet. The same is true for electrons, atoms, and even some large molecules. This wave-particle duality suggests that particles do not travel as tiny billiard balls, but as probabilities smeared out across space until they are observed. Then their wave-like spread collapses into a definite location. This strange dual identity is not just an oddity. It is at the heart of quantum mechanics. It means that what we think of as solid and localized is in truth part of a larger fluid pattern that only sharpens when we look. The phenomenon shows us that nature does not fit neatly into the categories we invented for everyday objects, and forces us to accept that the universe operates on rules far more flexible than common sense would suggest. Fact 3. Simply watching can change how reality unfolds. In the quantum world, observation is not passive. The very act of measuring a particle can change its state. In the famous double-slit experiment, photons or electrons form wave-like patterns when left alone, but switch to particle-like behavior when their paths are observed. It is as if nature knows when we are watching, though physicists explain it as the unavoidable interaction between the measuring device and the system. Still, this raises profound questions. If every measurement alters reality, then what is reality before the measurement? Is the world in a fuzzy in-between state until something forces it to choose? Whether you see it as a physical process or a philosophical puzzle, the idea that observation changes the outcome is one of the most mind-bending truths of quantum mechanics, and one that has fascinated and unsettled scientists for over a century. The implications stretch far beyond the laboratory. They touch on the nature of knowledge, the limits of what can be known, and whether reality exists in a definite form when no one is looking at it. Fact 4. Nature forbids us from knowing everything about a particle. Classical physics promised that if you measured precisely enough, you could know everything about a system, its position, speed, future path. Quantum mechanics says otherwise. The Heisenberg uncertainty principle tells us that there are limits to what we can know at the same time. For example, the more precisely you know a particle's position, the less precisely you can know its momentum and vice versa. This is not a flaw in our instruments, it is a built-in feature of nature itself. Particles simply do not have exact values for certain pairs of properties at the same time. The uncertainty is real and unavoidable. This means that at the quantum level, the future can never be predicted with perfect accuracy. All we can do is calculate probabilities, a shift in thinking that transformed science and challenged our deepest assumptions about determinism. The principle shows that the universe at its most basic level refuses to be pinned down completely, leaving room for randomness and unpredictability woven into the fabric of existence itself. Fact 5. A particle can exist in many states at once. Superposition is one of the strangest concepts in quantum physics. The idea that a particle can exist in multiple states or locations at the same time. An electron can spin up and down simultaneously, or a photon can take several paths at once. These states exist in a delicate balance described by a mathematical wave function. Only when a measurement is made does the particle choose one outcome and the superposition vanishes. This is not just theory. Experiments confirm it again and again. Quantum computers exploit superposition to perform many calculations in parallel, giving them immense potential power. In everyday life, superposition is impossible to see directly because it collapses the moment we interact with it. Yet at the quantum scale, it is the norm, a reminder that our everyday reality is just one version pulled from a swirling cloud of possibilities. The concept challenges everything we think we know about how objects exist and behave, suggesting that before we look, particles do not commit to being any one thing, but rather hold all options open at once. Fact 6. Reality is built from probabilities, not certainties. In the quantum realm, nothing is certain until it happens. A particle's position, momentum, or spin is not fixed ahead of time. It is described by a set of probabilities. These probabilities are encoded in the particle's wave function, which evolves smoothly until an interaction or measurement occurs. Only then does one outcome emerge chosen, seemingly at random from the possible ones. This probabilistic nature is not due to ignorance, but is fundamental to the way the universe works. Even with perfect knowledge of the wave function, you can only predict likelihoods, never guarantees. But over a century of experiments has shown that at the smallest scales, probability is not a sign of incomplete knowledge. It is reality itself. The shift from certainty to chance marked a revolution in how science understands the cosmos, and opened questions about free will randomness and the nature of truth that philosophers and scientists still debate today. Fact 7. How possibilities collapse into reality is still a mystery. We know that a quantum system can exist in many possible states at once, and that measurement somehow reduces these possibilities to a single outcome. But exactly how this collapse happens, or if it is even real, remains one of the biggest puzzles in physics. Some interpretations suggest collapse is a physical process triggered by observation. Others claim that all possibilities happen, but we experience only one branch of a larger multiverse. Another view says collapse is just an illusion, and the wave function never truly reduces at all. Despite decades of debate, no consensus exists. What is certain is that this moment, the shift from many possibilities to one, is central to our experience of reality. Understanding it may require not just new physics, but a deeper grasp of the nature of consciousness and the limits of knowledge. The mystery sits at the intersection of physics, philosophy, and perhaps even biology, waiting for a breakthrough that could reshape how we think about existence itself. Fact 8. Schrödinger's cat is alive and dead until you look. In 1935, physicist Erwin Schrödinger proposed a thought experiment to show how strange quantum superposition can be when applied to everyday objects. Imagine a cat in a sealed box with a device that has a 50-50 chance of releasing poison based on the decay of a single atom. Quantum theory says the atom is in a superposition of decayed and not decayed until measured, and so in principle, the cat is both alive and dead at the same time. Only when you open the box does the superposition collapse into one outcome. Schrödinger did not mean we should take this literally for cats. He meant to highlight the absurdity of quantum rules in the macroscopic world. Yet his famous cat remains one of the clearest, most enduring ways to picture the weirdness of quantum mechanics. The paradox shows how bizarre the quantum world becomes when we try to apply its logic to things we can see and touch, and it raises the question of where exactly the boundary lies between the quantum realm and our everyday experience. Fact 9. Two particles can share the same existence across space. Entanglement is one of the most baffling features of quantum mechanics, a phenomenon where two particles become so deeply linked that their states are no longer separate. Measure one and the other's properties snap into place instantly no matter how far apart they are. It is as though they are not two particles at all but one system stretched across space. This connection does not fade with distance, and it does not rely on signals travelling between them in the normal way. Once entangled, the particles share a kind of joint identity. Physicists have created entanglement in labs with photons, electrons, and even small groups of atoms. It is a fragile link easily broken by outside interference. Yet when preserved, it hints at a deeper layer of reality, one where separation is an illusion, and the universe is more interconnected than we can see. Entanglement challenges the idea that objects have independent properties, and suggests that at the quantum level, everything may be part of a single unified whole. Fact 10. Touch one particle here and another responds instantly far away. If you take two entangled particles and send them to opposite sides of the planet, something extraordinary happens. Measuring one instantly determines the state of the other, even if they are so far apart that, like the fastest thing in the universe, could not carry a message between them in time. This happens even if they are light years away. It is not that information travels faster than light. Rather, the two particles do not have independent states to begin with. They are in a sense the same thing. This instantaneous connection has been tested again and again in laboratories with distances stretching from meters to hundreds of kilometers. The results always match quantum theory's predictions, no matter how counterintuitive they seem. It is a reminder that our everyday notions of cause-effect and distance may not apply in the deepest workings of nature. The phenomenon suggests that space itself may not be as fundamental as we think, and that the true structure of reality might be something entirely different. Fact 11. Even Einstein was disturbed by this quantum link. Albert Einstein famously disliked the idea of entanglement. He called it spooky action at distance, convinced that it must be an incomplete description of reality. In his view, there had to be hidden variables, unseen factors that would explain the strange correlations between particles without invoking faster-than-light effects. Along with Boris Podolsky and Nathan Rosen, he proposed a thought experiment in 1935, now known as the EPR paradox, to challenge quantum mechanics. They argued that if quantum theory was correct, it implied either impossible communication between distant particles, or that the particles did not have definite properties until measured, both of which felt absurd. Decades later, experiments proved that entanglement is real and cannot be explained by hidden variables alone. Ironically, Einstein's own challenge helped inspire the research that confirmed quantum mechanics' most mysterious feature. His discomfort with the theory shows how even the greatest minds can struggle with ideas that defy intuition, and it reminds us that nature does not always conform to what seems reasonable or comfortable. Fact 12. Experiments show this connection is real and unbreakable. For decades, entanglement remained a theoretical puzzle. Then, starting in the 1970s, physicists began designing experiments to test it directly. Using pairs of photons, they measured the correlations between them and compared the results with the predictions of quantum mechanics versus classical hidden variable theories. The results were decisive. Quantum mechanics won. Since then, the tests have grown ever more precise, closing loopholes and extending the distances between entangled particles. In 2017, scientists sent entangled photons between ground stations and a satellite in orbit, confirming the effect over more than 1,000 kilometers. Each success strengthens the conclusion. Entanglement is not just a quirk of the lab. It is a fundamental feature of reality, And as strange as it seems, the universe allows this perfect connection to exist without any visible link at all. The confirmation of entanglement over such vast distances opened the door to practical applications like quantum communication and highlighted just how deeply interconnected the universe really is. Fact 13. No hidden mechanism explains these strange correlations. Einstein hoped that entanglement could be explained by hidden variables, secret information carried by particles that predetermines their behavior. But in the 1960s, physicist John Bell devised a mathematical test to tell whether such variables could exist. His result, known as Bell's theorem, showed that if hidden variables were real, the correlations between entangled particles would be limited in specific ways. Quantum mechanics predicted stronger correlations and experiments consistently found them. This means that no theory relying solely on hidden local information can fully explain what is happening. The universe at its core does not behave according to the tidy deterministic rules Einstein envisioned. Instead, it behaves in a way that suggests reality is more deeply connected and perhaps less local than we ever imagined. Bell's theorem proved that the strangeness of quantum mechanics is not just a mathematical quirk, but a reflection of how nature truly operates, forcing us to accept that the universe is weirder than classical physics ever allowed. Fact 14. Bell's theorem proved the universe does not behave classically. Bell's theorem is one of the most profound discoveries in physics. It does not just say that quantum mechanics is weird. It says that if the theory is correct, then the universe itself cannot be explained by any classical model that relies on local causes. The fact that experiments match quantum predictions means that nature either allows instantaneous influences across distance, or it abandons the idea that objects have definite properties before we measure them. Either way, it forces us to rethink what is real and how reality is structured. Bell's work, once a niche subject, has now become central to quantum information science, laying the groundwork for technologies like quantum cryptography and secure communication, all built on the very spooky action that Einstein doubted. The theorem stands as a monument to the power of theoretical reasoning and experimental verification, showing that nature can surprise us in ways that challenge our deepest assumptions about how the world works. Fact 15. Quantum teleportation sends a particle's identity elsewhere. Quantum teleportation is not like science fiction. It does not move objects through space in an instant. Instead, it transfers the state of one particle to another using entanglement as the bridge. First two particles are entangled. One is sent to the destination while the other stays with the sender. By performing a special joint measurement on the sender's particle, and the particle to be teleported, the quantum state is destroyed in one place and recreated in the other. No physical matter travels, but the exact quantum information does. This process has been demonstrated with photons, atoms, and ions over distances ranging from a few meters to hundreds of kilometers. It is a key ingredient for building quantum networks. And though it will not beam humans across space, it does something equally magical. It lets the identity of a quantum system leap from one location to another. The technique could revolutionize communication and computing by enabling perfectly secure data transfer and distributed quantum processing across global networks. Fact 16. Some think space-time emerges from entanglement. In recent years, a bold idea has gained attention, that the very fabric of space-time might be woven from quantum entanglement. According to this view, the geometry of space, the distances, curves, and connections between points, could be the large-scale expression of countless microscopic quantum links. If true, this would mean that gravity and the shape of the universe are not fundamental, but emerge from a deeper layer of quantum information. Theoretical studies in areas like holographic duality and tensor networks hint at how such a connection might work. While still speculative, this idea could unite general relativity and quantum mechanics into a single framework and reveal that without entanglement, space itself might unravel. The concept suggests that the universe is not a stage on which events occur, but rather a pattern of relationships between quantum systems, with distance and geometry arising naturally from how those systems are connected. It is one of the most exciting frontiers in theoretical physics today. Fact 17. The universe may be woven together by quantum links. If entanglement is as universal as quantum theory suggests, then it is not just a laboratory oddity. It is happening everywhere all the time. particles produced together in distant stars, ancient cosmic events, or even the Big Bang itself may still be connected by invisible threads. In this sense, the universe is less like a collection of separate objects and more like a single seamless whole. These connections may fade when disturbed, but new ones form constantly as particles interact. The idea that reality is stitched together in this way challenges the picture of the cosmos as a vast emptiness dotted with isolated points of matter. Instead, everything may be part of a single ongoing quantum conversation written in the shared language of entanglement. This vision of the universe as a web of relationships rather than a collection of things transforms our understanding of what it means for something to exist, and suggests that separation itself may be an illusion created by our limited perspective. Fact 18. Entangled particles can keep their bond against all odds. Entanglement is delicate. It can be destroyed by heat, noise, or interactions with the environment. Yet in some conditions it can persist in surprising ways. Certain systems like superconductors and Bose-Einstein condensates can hold vast numbers of particles in entangled states that endure for long periods. Even in the messy, noisy world outside, the lab traces of entanglement have been observed between particles separated by significant distances. This resilience makes entanglement not just a fragile curiosity, but a potential resource for real-world technologies. If we learn to protect and control it, we could harness these enduring bonds to power quantum communication, computing, and sensing on a scale that transforms how we share and process information. Researchers are developing techniques to shield entangled states from decoherence using error correction codes and specially designed materials, bringing the dream of practical quantum technology closer to reality with each breakthrough. Fact 19. Electrons are infinitely small yet spread out like clouds. An electron is one of the most familiar subatomic particles. It flows through wires, binds atoms together, and shapes the chemistry of life. Yet when scientists try to measure its size, they find something baffling. It behaves as if it has no internal structure and no measurable diameter. At the same time, it does not act like a pinpoint. Instead, its presence is smeared out in a cloud of probability surrounding the atomic nucleus in patterns shaped by quantum rules. This electron cloud is not a physical fog, but a map of where the electron is most likely to be found. In one moment it might be near the nucleus, in the next far away, and it is impossible to predict exactly where until you look. This dual nature, both point-like and spread out, is a perfect example of how quantum particles defy our everyday intuition. The electron's behavior shows that matter at the smallest scales does not occupy space in the way we expect, existing instead as a blur of potential locations that only becomes definite when observed. Fact 20. Weightless photons can still push objects around. Photons, the particles of light, have no mass, yet they carry energy and momentum. This means they can exert pressure when they strike an object, a phenomenon known as radiation pressure. In space where there is no air to resist movement, this tiny push can have a big effect over time. Sunlight can slowly alter the paths of dust grains, asteroids, and even spacecraft. Engineers have even designed solar sails, vast mirror-like sheets that use the momentum of sunlight to propel them, requiring no fuel at all. On smaller scales, focused beams of light can trap and move microscopic objects, a technique called optical tweezers which is used in biology and nanotechnology. That something with no rest mass can physically move matter is one of light's most surprising and useful quantum gifts. The phenomenon demonstrates that energy and momentum are deeply connected, and that even the gentlest touch of light carries with it a tangible physical force. Fact 21. Billions of ghostly neutrinos pass through you every second. Every moment, without you feeling a thing, countless neutrinos are streaming through your body. These nearly massless particles are created in enormous numbers by the sun, distant stars, exploding supernovae, and even radioactive decay in Earth's crust. Neutrinos interact so weakly with matter that they can pass through entire planets as if they were empty space. Trillions of them are flowing through Earth and you at any given moment, yet detecting them is incredibly difficult. Huge underground detectors filled with ultra-pure liquids or ice wait patiently for the rare event when a neutrino collides with an atom. Studying them can reveal secrets about how stars work, how the universe evolved, and even whether matter and antimatter are perfectly symmetrical. Invisible, almost intangible, Neutrinos are proof that the cosmos is full of hidden motion and energy we barely notice. They remind us that the universe is far more active than our senses suggest, and that reality contains layers of phenomena that pass through us constantly without leaving a trace. Fact 22. Quarks are forever trapped in groups of 2 or 3. Quarks are the fundamental building blocks of protons and neutrons and therefore of most of the matter we see. But unlike electrons, quarks are never found alone. They are confined by the strong nuclear force mediated by particles called gluons. This force grows stronger as quarks are pulled apart, much like stretching a rubber band that resists more and more. Try to separate quarks and the energy you add will eventually create new quark pairs, which immediately bind into new particles. This phenomenon known as confinement means that quarks are forever locked together in groups of 2 called mesons or 3 called baryons. It is as if nature has decreed that quarks can never be solitary travellers. They exist only as parts of a greater whole bound in the heart of every atom's nucleus. The confinement of quarks is so absolute that no experiment has ever isolated a single quark, making them unique among fundamental particles in their inability to exist independently. Fact 23. Gluons hold the strongest bonds in the universe. The strong nuclear force is the most powerful of nature's 4 fundamental forces, and gluons are its carriers. Their name comes from their role gluing quarks together to form protons, neutrons, and other particles. But gluons are unlike the force-carrying particles in electromagnetism or gravity. They not only interact with quarks, but also with each other, creating a dense self-binding network that traps quarks inside. This makes the strong force so intense that breaking a single proton apart would require energies far beyond anything we can produce on Earth outside of particle accelerators. Without gluons, atoms and the matter they form could not exist. In a very real sense, gluons are the hidden threads that keep the universe stitched together at its smallest scales. The self-interacting nature of gluons makes the strong force behave in ways that are fundamentally different from other forces, creating a level of binding strength that ensures the stability of atomic nuclei and the matter built from them. Fact 24. Without the Higgs boson, mass would not exist. The Higgs boson discovered in 2012 at CERN's Large Hadron Collider was the missing piece of the standard model of particle physics. It is associated with the Higgs field, an invisible energy field that permeates all of space. As particles move through this field, they interact with it, and this interaction gives them mass. Without the Higgs, field particles like quarks and electrons would have no mass, and atoms, planets, and life could never form. The Higgs boson itself is a quantum ripple in the Higgs field detectable only in high-energy collisions. Its discovery confirmed a decades-old theory and earned François Engler and Peter Higgs the Nobel Prize. It also provided a profound answer to a simple question: why does anything weigh anything at all? The Higgs mechanism shows that mass is not an intrinsic property of particles, but rather emerges from their interaction with an underlying field, fundamentally changing how we understand the origin of matter's most basic characteristic. Fact 25. Empty space boils with fleeting virtual particles. Even in perfect vacuum space is not truly empty. Quantum field theory predicts that pairs of particles and antiparticles constantly flicker into existence, borrowing energy from the vacuum before annihilating and disappearing again. These virtual particles cannot be observed directly, but their effects can be measured. For example, they cause tiny shifts in the energy levels of electrons in atoms and produce forces between objects in vacuum, known as the Casimir effect. This constant bubbling of activity means that empty space is more like a restless ocean than a still void. The idea that nothing is actually full of temporary unseen particles is one of the strangest and most confirmed predictions of quantum physics. The phenomenon shows that the vacuum is not passive emptiness, but an active dynamic medium where quantum fluctuations create brief disturbances that leave measurable fingerprints on the behavior of real particles and the structure of space itself. Fact 26. The quantum vacuum is bursting with energy. All those fleeting virtual particles in the vacuum carry energy called zero-point energy that exists even when a system is at its lowest possible energy state. In principle, every cubic centimetre of empty space contains an enormous amount of this energy. Most of it cancels out or remains inaccessible, but its effects can still be detected in subtle ways, such as in the behavior of atoms and the expansion of the universe. In cosmology, some scientists suspect that dark energy, the mysterious force driving cosmic acceleration, may be linked to vacuum energy. The paradox is that theoretical calculations predict a vacuum energy vastly larger than what we observe, suggesting we still do not fully understand one of the most fundamental ingredients of reality. The mismatch between prediction and observation is so huge that it represents one of the greatest unsolved problems in all of physics, hinting that something profound about the nature of space and energy remains hidden from us. Fact 27. Antimatter is matter's perfect but opposite twin. For every type of particle there exists an antiparticle with the same mass, but opposite charge and other properties. When a particle meets its antiparticle, they annihilate in a burst of pure energy. Antimatter was predicted by Paul Dirac in 1928 and discovered in cosmic rays soon after. It is rare in the universe today. Most was destroyed in mutual annihilations shortly after the Big Bang. Why matter survived while antimatter mostly vanished remains one of the great unsolved mysteries of physics. We can create antimatter in particle accelerators and even trap small amounts. But storing it is challenging because it annihilates on contact with matter. Antimatter is not just a curiosity, it has potential applications in medicine such as in PET scans, and in future propulsion systems that could in theory harness its incredible energy density. The existence of antimatter shows that nature has a kind of mirror symmetry at the particle level, though the universe itself appears to have broken that symmetry long ago. Fact 28. Matter can be created from pure energy and erased back. Einstein's famous equation E equals mc squared tells us that mass and energy are two forms of the same thing. Under the right conditions, energy can transform into matter, and matter back into energy. High-energy collisions like those in particle accelerators or near black holes can produce particle-antiparticle pairs from pure energy. Conversely, when particles meet their antiparticles, they annihilate into photons. This constant interchange between mass and energy plays out throughout the cosmos, in the hearts of stars, in the early universe, and in extreme astrophysical events. It shows that matter is not a permanent solid substance. It is a form energy can take, briefly shaped into particles before returning to light. The ability to convert between matter and energy reveals that these two seemingly different things are actually manifestations of a single underlying reality, demonstrating one of the deepest unifications in all of physics. Fact 29. Every particle is just a ripple in an invisible field. According to quantum field theory, the universe is not made of particles floating in empty space. It is made of underlying fields that stretch everywhere. Each type of particle is simply a localized vibration or ripple in its own field. Electrons are ripples in the electron field, photons are ripples in the electromagnetic field, and so on. Even when there are no particles present, the fields themselves still exist, filling all of space. This way of thinking unites matter and energy, showing them as different expressions of the same underlying fabric. It also means that particles are not tiny indivisible marbles. They are events, disturbances in something deeper and more fundamental. Wherever you are, these invisible fields are right. They're quietly shaping everything you see, touch, and experience. The field picture of reality suggests that what we call empty space is actually filled with potential, waiting for the right conditions to produce the particles and forces we observe. Fact 30. Quantum field theory merges particles and forces into one. Before quantum field theory, particles and forces were treated as separate things, objects that interacted through invisible influences. But quantum field theory revealed that forces themselves arise from fields, and their effects are carried by particles. In electromagnetism, for example, the electromagnetic field produces photons which mediate the force between charged particles. The strong nuclear force emerges from the gluon field, and the weak nuclear force from the W and Z boson fields. Even gravity may one day be described this way, though a complete quantum theory of gravity still eludes us. Quantum field theory is one of the most successful frameworks in all of science, with predictions confirmed to extraordinary precision. It is our best description of reality at the smallest scales, a single language for both the matter that exists and the forces that move it. The unification it provides represents one of the crowning achievements of 20th century physics. Fact 31. Even the emptiest space is alive with activity. If you imagine the vacuum of space as cold, empty nothingness, quantum physics invites you to think again. Even without particles, fields are never perfectly still. They quiver with constant fluctuations, producing brief appearances of virtual particles that vanish as quickly as they arrive. This restless background is present everywhere, between the stars, inside atoms, even in the vacuum of your living room. It is an energy that cannot be turned off. And though most of it is hidden, it leaves measurable fingerprints in experiments. The fact that nothing is actually a seething active medium changes the way we think about space. It is not an empty stage for reality to unfold on. It is part of the cast quietly shaping the drama at every moment. The quantum vacuum shows that emptiness is not really empty at all, but filled with invisible activity that influences everything, from the behavior of particles to the structure of space-time itself. Fact 32. A perfect vacuum can pull objects together. It sounds like science fiction. Place two uncharged metal plates very close together in a vacuum, and they will slowly drift toward each other. This is the Casimir effect, a direct consequence of quantum vacuum fluctuations. The space between the plates allows only certain wavelengths of virtual particles to exist, while the space outside allows more. This difference in pressure pushes the plates inward. The effect is incredibly small, but it has been measured in laboratories and confirms that the vacuum is not empty at all. Though it has no practical use yet, the Casimir effect is a striking reminder that quantum forces can emerge from what we think of as nothing, shaping the motion of real physical objects. The phenomenon provides some of the clearest evidence that the quantum vacuum is not merely a theoretical concept, but a physical reality with tangible consequences that can be observed and measured in controlled experiments. Fact 33. Zero-point energy exists everywhere in the universe. Even when a system is in its lowest possible energy state with no heat, no motion, no light, it still contains a residual amount of energy called zero-point energy. This is a direct result of the uncertainty principle. You cannot have a field with zero energy because that would mean knowing both its position and momentum exactly. Zero-point energy is tiny on human scales, but because it exists everywhere, it may add up to something enormous across the cosmos. Some theories suggest it could be linked to the mysterious dark energy driving the universe's accelerated expansion. Whether or not that is true, zero-point energy is one of the clearest examples of how quantum physics says empty space is never truly empty. The concept shows that absolute stillness is impossible in a quantum universe, and that even at the coldest temperatures and in the most isolated systems, there remains an irreducible background of energy. Fact 34. Empty space can warp gravity and time. In Einstein's theory of general relativity, mass and energy tell space-time how to curve, and curvature tells matter how to move. If the vacuum is full of quantum energy, then even empty space can shape the geometry of the universe. This means that quantum effects may subtly influence gravity and perhaps time itself. In principle, the density of vacuum energy could change how the universe expands, how galaxies form, and even how time flows in extreme conditions. The exact nature of this interaction is still a mystery, partly because combining quantum theory and gravity into a single framework remains one of the hardest problems in physics. But it is possible that the key to understanding cosmic evolution lies hidden in the structure of empty space. The interplay between quantum mechanics and gravity at the level of the vacuum could hold answers to some of the deepest questions about the origin and fate of the universe. Fact 35. Powerful fields can twist the nature of the vacuum. The vacuum might feel unchangeable, but under extreme conditions it can transform. Very strong electric or magnetic fields can polarize the vacuum, aligning its virtual particles in ways that alter its properties. In theory, if the fields are intense enough, they could even cause the vacuum to break down, producing real particle-antiparticle pairs out of the energy. This phenomenon, called vacuum decay, has not been observed directly. The required fields are beyond anything we can currently generate, but its effects are predicted by quantum electrodynamics. Such behavior means that the vacuum is not a passive backdrop, but an active dynamic medium that can respond to its environment in surprising ways. The possibility of vacuum polarization and breakdown shows that what we call empty space has structure and properties that can be manipulated, suggesting that the vacuum is more like a material substance than absolute nothingness. Fact 36. Black holes glow by stealing energy from empty space. Black holes are famous for letting nothing escape, not even light. Yet quantum theory predicts that they can slowly radiate energy, a process called Hawking radiation. Near the event horizon, vacuum fluctuations constantly create pairs of virtual particles. Normally these particles annihilate quickly, but at a black hole's edge one particle can fall in while the other escapes. To an outside observer, it looks as though the black hole is emitting radiation, slowly losing mass over time. This process is incredibly faint for large black holes, but it is a profound insight. Quantum physics suggests that even the darkest, most inescapable objects in the universe are not completely black. The discovery of Hawking radiation showed that black holes have temperature and entropy, connecting thermodynamics with quantum mechanics and gravity in a way that hints at deeper unification. It also means that black holes are not eternal, but will eventually evaporate completely over unimaginably long timescales. Fact 37. The energy of nothingness may be driving the universe apart. In 1998, astronomers discovered that the expansion of the universe is accelerating. The cause is unknown, but one leading candidate is dark energy, a form of energy that seems to be built into space itself. If dark energy is real, it behaves much like vacuum energy, exerting a constant outward pressure. Over billions of years, this force could stretch the universe so far that distant galaxies slip forever beyond our reach. The idea that the ultimate fate of the cosmos might be determined by the energy of empty space is one of the most haunting results to come from modern physics. If dark energy continues to dominate the universe's expansion, then in the far future, the cosmos will become an increasingly cold, dark and lonely place, with galaxies isolated from one another across unbridgeable distances, a scenario cosmologists call the Big Freeze or heat death. Fact 38. The true nature of the quantum vacuum remains unknown. We can describe the quantum vacuum mathematically, measure its effects in experiments, and even connect it to cosmic scale phenomena. But we still do not truly understand what it is. Is it a physical medium like an invisible ocean filling space? Is it a property of fields that exist whether or not particles are present? Or is it something even stranger, perhaps tied to the origin of the universe itself? The vacuum sits at the intersection of quantum theory, relativity and cosmology, three pillars of physics that still resist full unification. Until we understand it completely, the emptiness between the stars will remain one of the most profound and mysterious aspects of reality. The vacuum may hold the key to understanding why the universe exists at all, and why it has the properties and laws that allow for complexity, structure, and ultimately life. Fact 39. Quantum computers can think in many realities at once. Unlike classical computers which process information in binary bits that are either 0 or 1, quantum computers use qubits, units that can exist in superpositions of 0 and 1 at the same time. This allows them to explore many possible solutions simultaneously, as if they are testing outcomes across multiple realities before settling on an answer. The power of this approach grows exponentially with the number of qubits making certain problems that would take classical computers millennia potentially solvable in seconds. Quantum computers are still in their infancy, struggling with error correction and stability. But even now they hint at a future where problems in chemistry, cryptography, and optimization could be cracked with breathtaking speed. It is not magic. It is the quantum rules of probability and interference harnessed in a way that classical logic could never match. The development of quantum computers represents one of the most ambitious technological projects of our time, with the potential to revolutionize fields from drug discovery to artificial intelligence. Fact 40. Qubits can store multiple answers in a single moment. A qubit is not locked into a single state until it is measured. Before then, it can hold a blend of possibilities, both 0 and 1, weighted by probabilities. This property is what gives quantum computers their massive potential power. With just a handful of qubits, you can represent an astronomical number of possible combinations at once. When a quantum algorithm runs, it manipulates these probabilities in a carefully choreographed way so that the wrong answers cancel each other out and the correct one remains. It is like searching an entire library in parallel instead of book by book. The catch is that measurement collapses a qubit's state, so designing algorithms that extract useful results from this delicate superposition is one of the central challenges in quantum computing. The fragility of qubits means that quantum computers must operate at extremely low temperatures and in carefully isolated environments to prevent decoherence from destroying the quantum states before calculations are complete. Fact 41. Entanglement supercharges quantum processing. Entanglement is not just a curiosity, it is a resource. In quantum computing, entangled qubits share correlations that classical bits never could, allowing operations on one qubit to instantly influence its entangled partners. This enables quantum computers to perform complex computations more efficiently, linking distant parts of a problem together without moving physical information around. Entanglement also plays a role in error correction, helping detect and fix mistakes without directly observing the qubit's fragile states. Without entanglement, quantum computers would lose much of their advantage over classical machines. It is the invisible thread that ties their logic together, giving them the power to tackle problems far beyond the reach of today's fastest supercomputers. The ability to create, maintain, and manipulate entanglement between multiple qubits is one of the key technical challenges in building practical quantum computers, requiring exquisite control over quantum systems and their environments. Fact 42. Certain quantum algorithms could solve problems instantly. Some quantum algorithms are so efficient that they could in principle crack problems that would stump classical computers for centuries. One famous example is Shor's algorithm, which can factor large numbers exponentially faster than the best-known classical methods, a breakthrough that could undermine many of today's encryption systems. Another is Grover's algorithm, which can speed up database searches in a way no classical approach can match. These algorithms do not make quantum computers universally faster, but for the problems they are suited to, the advantage can be enormous. This is why governments, tech companies, and researchers are racing to develop practical quantum processors. The first to do so will unlock computational capabilities that could reshape technology and security. The potential for quantum computers to break current encryption has sparked a race to develop quantum-resistant cryptography before large-scale quantum computers become available. Fact 43. Quantum cryptography creates secrets that cannot be cracked. Classical cryptography relies on the difficulty of certain mathematical problems, but in theory, a powerful enough computer could break them. Quantum cryptography, by contrast, uses the laws of physics to guarantee security. The most famous method, quantum key distribution, sends encryption keys encoded in the states of photons. Any attempt to eavesdrop inevitably disturbs these states, revealing the intrusion instantly. This means that secure communication is possible even over channels an attacker can fully observe. Quantum cryptography has already been tested in real-world networks, including satellite links, and could one day protect financial transactions, government communications, and personal data with a level of security no classical system can match. The fundamental impossibility of copying quantum states without detection means that quantum cryptography offers security based not on computational difficulty but on the laws of nature themselves, providing protection that cannot be overcome by future advances in computing power. Fact 44. Quantum sensors detect the barest whispers of change. By exploiting quantum effects like superposition and entanglement, quantum sensors can measure quantities such as time, acceleration, and magnetic fields with extraordinary precision. They are so sensitive that they can detect changes too small for any classical instrument, shifts caused by tiny gravitational variations, subtle brain activity, or even the presence of dark matter particles. Some designs use clouds of ultra-cold atoms or nitrogen vacancy centers in diamond to achieve this sensitivity. In the future, quantum sensors could revolutionize navigation, medical imaging, and geological surveying, opening new windows into both the human body and the Earth itself. The ability to measure with quantum precision could enable new forms of medical diagnosis that detect diseases earlier, navigation systems that work without GPS satellites, and searches for new physics beyond the standard model through detection of minute forces and fields. Fact 45. Superconductors let electricity flow forever without loss. Normally electric currents face resistance, converting some of their energy into heat. But in certain materials cooled to extremely low temperatures, resistance drops to zero, a state called superconductivity. In this state, electrons pair up and flow without losing any energy, potentially forever. This phenomenon is quantum in nature, relying on the collective behavior of countless particles acting as a single coherent wave. Superconductors are already used in MRI machines, particle accelerators, and magnetic levitation trains. But if we could achieve superconductivity at room temperature, it would revolutionize energy transmission, eliminating waste and enabling entirely new technologies. The search for room temperature superconductors is one of the holy grails of condensed matter physics, with the potential to transform power grids, transportation, and countless other applications by allowing loss-free transmission of electricity over any distance. Fact 46. Quantum networks could connect computers across the globe. Just as classical computers are linked by the Internet future, quantum computers could be joined by quantum networks. These networks would use entanglement and quantum teleportation to transmit information in a way that is impossible to intercept without detection. Building such a network requires creating and maintaining entanglement over long distances, something researchers are already testing using optical fibers, satellites, and quantum repeaters. A fully functional quantum internet could enable ultra-secure communications, distributed quantum computing, and new forms of sensing that work across vast distances, essentially turning the entire planet into a single interconnected quantum system. The quantum internet would not replace the classical internet but complement it, providing capabilities for secure communication and distributed quantum computation that are fundamentally impossible with classical technology alone. Fact 47. Atomic clocks keep time so well they barely drift in billions of years. The most accurate timekeepers in the world are atomic clocks which use the natural vibrations of atoms, often cesium or ytterbium, as their ticks. In advanced versions, atoms are cooled to near absolute zero and held in place by lasers, allowing their oscillations to be measured with incredible precision. The best atomic clocks would gain or lose less than a second over the entire age of the universe. Such precision is not just academic. It is crucial for GPS navigation, telecommunications, and scientific experiments. Quantum advances are pushing this accuracy even further to the point where atomic clocks might soon detect changes in the passage of time caused by tiny differences in gravitational potential. The extreme precision of atomic clocks has already allowed tests of Einstein's theory of relativity at unprecedented levels, and may one day enable detection of gravitational waves or searches for variations in fundamental constants. Fact 48. Quantum technology is already reshaping science. While quantum computers often grab headlines, quantum technology is already at work in many areas of research and industry. Quantum sensors are mapping underground structures, quantum communication links are securing test networks, and quantum simulators are helping scientists model complex molecules and materials. These tools are not science fiction. They are practical applications of quantum mechanics that are expanding our capabilities today. As the technology matures, it is likely to influence fields from climate modeling to drug discovery, giving us new ways to understand and shape the world. The quantum revolution is not coming someday. It is already here, quietly changing the way we explore reality. From improving medical imaging to designing new materials, quantum technology is beginning to deliver on the promise of harnessing quantum mechanics for practical benefit, with many more applications expected as the technology continues to develop. Fact 49. The Copenhagen interpretation says reality is not real until measured. The Copenhagen interpretation, developed in the 1920s by Niels Bohr and Werner Heisenberg, remains one of the most widely taught explanations of quantum mechanics. It suggests that a quantum system does not have definite properties until it is measured. Before that moment, it exists in a superposition, a blend of all possible outcomes. The act of measurement forces the system into a single state, collapsing the wave function. This view is practical, matching experimental results perfectly, but it is philosophically unsettling. Does reality truly depend on observation to exist in a definite form? Or is the collapse just a mathematical shortcut we use because we cannot track every quantum detail? The Copenhagen interpretation leaves these questions open, accepting uncertainty as a fundamental part of the universe, not a flaw to be fixed. Despite its widespread use, the interpretation remains controversial because it seems to give observation a special role in determining reality, raising questions about what counts as an observation and whether reality exists independently of measurement. Fact 50. The many worlds view suggests every outcome actually happens. Proposed by Hugh Everett in 1957, the many worlds interpretation sidesteps the problem of wave function collapse entirely. Instead, it says that when a quantum event has multiple possible outcomes, all of them occur, but in separate branching universes. If a particle could go left or right, the universe splits, creating one version where it goes left and another where it goes right. In this view, reality is an ever-growing tree of possibilities, with countless versions of ourselves living out different histories. While this neatly preserves the equations of quantum mechanics without mysterious collapse, it raises staggering questions. If all outcomes happen, what does it mean to make a choice? And could these parallel worlds ever interact or be observed? The many worlds interpretation is appealing to some physicists because it takes the mathematics of quantum mechanics completely seriously without adding extra assumptions about collapse. But it comes at the cost of accepting an unimaginably vast multiverse of parallel realities. Fact 51. Pilot wave theory gives particles hidden paths to follow. Pilot wave theory, also called Bohmian mechanics, offers a more deterministic picture of the quantum world. It proposes that particles always have definite positions and velocities, guided by a pilot wave that evolves according to the Schrödinger equation. The strange wave-like interference patterns we see in experiments arise not because particles are smeared out in space, but because this guiding wave influences their trajectories. Pilot wave theory reproduces all the predictions of standard quantum mechanics, but adds hidden variables, unseen details that determine exactly how each particle moves. It is an appealing idea for those uncomfortable with randomness, though it requires accepting non-local effects where distant events can influence each other instantly. The theory suggests that quantum randomness is not fundamental, but emerges from our ignorance of the pilot wave's precise configuration, offering a vision of reality that is fully deterministic underneath its probabilistic appearance. Fact 52. Collapse theories say quantum states can end themselves. Collapse theories propose that superpositions do not last forever, even without measurement. They eventually decay into a single outcome. In these models, quantum states evolve normally for a time, but have a small chance per unit time to collapse spontaneously. For small systems like atoms, this chance is tiny, allowing superpositions to persist. For larger systems, the collapse happens so quickly that we never notice superpositions in our everyday world. These theories aim to explain why we do not see quantum strangeness at human scales without invoking conscious observers or parallel universes. Experiments are underway to test collapse models by looking for faint random energy releases that would signal a spontaneous reduction of the wave function. If collapse theories are correct, then the transition from quantum to classical behavior is not just about decoherence, but involves a genuine physical process that destroys superpositions at a fundamental level, providing a natural boundary between the quantum and classical realms. Fact 53. Decoherence explains why quantum strangeness disappears in big objects. Decoherence is not a separate interpretation, but a physical process that helps explain why quantum effects fade in large systems. When a quantum system interacts with its environment, air molecules, light, vibrations, information about its state leaks away into countless surrounding particles. This effectively measures the system, destroying the delicate interference patterns of superposition and making it behave more classically. Decoherence happens incredibly fast for macroscopic objects, which is why we never see them in visibly mixed states. While decoherence explains the transition from quantum to classical behavior, it does not solve the measurement problem. It still leaves open the question of how one outcome is chosen from the possible ones. The process shows that quantum behavior is not absent in large objects, but simply becomes unobservable as quantum information spreads into the environment, making it practically impossible to maintain the coherent superpositions needed to see quantum effects. Fact 54. The measurement problem still puzzles physicists. At the heart of quantum mechanics lies the measurement problem. How and why does a superposition become a single outcome when observed? The equations describe the evolution of a wave function smoothly over time, but say nothing about the sudden collapse into a definite state. Is this collapse a real physical process or just an apparent change in our knowledge? Interpretations from Copenhagen to many worlds to collapse theories each offer different answers, but none have been proven. The measurement problem is more than an abstract puzzle. It touches on the nature of reality itself and on whether the world exists in a definite state when no one is looking. Solving it may require not just new experiments, but a radical rethinking of what we mean by observation, reality, and the relationship between the two, potentially connecting physics to questions about consciousness and the nature of information. Fact 55. Could human awareness decide reality's fate? Some interpretations, often considered controversial, suggest that consciousness itself plays a role in collapsing the wave function. In this view, it is not just physical interaction with a measuring device that determines an outcome, but the awareness of an observer. This observer effect is sometimes overstated in popular culture, but the underlying idea has roots in discussions by physicists like John von Neumann and Eugene Wigner. While most scientists today favor purely physical explanations, the possibility that the mind could influence fundamental physical processes is tantalizing. Testing it is difficult, but the question lingers. Is reality shaped in part by our act of noticing it? The consciousness interpretation raises profound questions about the relationship between mind and matter, and whether subjective experience plays any role in the objective physical world, though most physicists remain skeptical that consciousness is necessary for wave function collapse. Fact 56. Quantum logic does not always obey common sense. In classical logic, statements are either true or false. There is no middle ground. But in the quantum world, logic works differently. Properties can be partly true and partly false at the same time, depending on the context of the measurement. The order in which you measure different quantities can change the outcome, something that never happens in classical physics. Quantum logic reflects the underlying mathematics of Hilbert space, where events are not just yes or no, but probabilities that can interfere with each other. This departure from everyday reasoning is one reason quantum mechanics feels so alien. It is not just that the world behaves strangely, it is that the very rules for describing it have to be rewritten. The non-commutative nature of quantum measurements means that asking questions in different orders can lead to different answers, fundamentally challenging our classical notions of how properties and observations should relate to each other. Fact 57. The universe might be fundamentally random at its core. In quantum mechanics, some events have no cause that can be predicted in advance, no matter how much information you have. The decay of a radioactive atom, the outcome of a particle measurement, these are fundamentally probabilistic. This is not randomness from ignorance, but randomness built into the fabric of reality. For some, this is unsettling, suggesting that the universe is not a clockwork machine, but a game of chance. For others, it is liberating, allowing for novelty and unpredictability, even in a world governed by laws. Whether randomness is truly fundamental, or just a reflection of deeper physics we have not discovered, remains one of the deepest questions in science. The question touches on free will, determinism, and whether the future is written in the present or genuinely open, with quantum indeterminacy potentially providing room for genuine novelty and creativity in the unfolding of events. Fact 58. Quantum physics may bend the rules of space and time. At extreme scales, quantum mechanics and relativity begin to collide, and the results suggest that space and time themselves might not be as fixed as we think. Quantum fluctuations can ripple through space-time, potentially creating tiny temporary distortions. Some theories of quantum gravity propose that space-time is made of discrete units like pixels in a cosmic screen, while others suggest that time could emerge from deeper timeless laws. In experiments with entangled particles, correlations appear to transcend normal limits of distance, and time hinting at connections that lie outside our familiar framework. If these ideas are right, then space and time are not the stage for reality. They are part of the cast, shaped by the same strange rules that govern the quantum world. The potential for space-time to be an emergent rather than fundamental feature of reality would represent one of the most profound shifts in our understanding of the universe. Fact 59. Superfluid helium can flow up walls without resistance. When helium is cooled below about 2 degrees above absolute zero, it undergoes a remarkable transformation into a state called a superfluid. In this state, it loses all viscosity, the internal friction that normally slows a liquid's flow. As a result, superfluid helium can creep up and over the sides of a container flowing against gravity in a thin film. It can pass through tiny pores that would block any ordinary liquid, and it can circulate endlessly in a closed loop without slowing down. This strange behavior comes from quantum mechanics acting on a macroscopic scale. The helium atoms all fall into the same quantum state, moving together as one perfectly coordinated wave. Superfluid helium shows that quantum effects normally confined to the microscopic world can sometimes spill over into forms we can see and touch, demonstrating that quantum coherence can persist even in systems containing billions of atoms. Fact 60. Bose. Einstein condensates behave like a single giant atom. Predicted in the 1920s by Satyendra Bose and Albert Einstein, Bose-Einstein condensates are formed when certain types of atoms are cooled to a fraction of a degree above absolute zero. At this temperature, the atom's individual wave functions overlap and merge, creating a single unified quantum state that spans the entire sample. In effect, the whole condensate behaves like one superatom, with all its particles moving in perfect synchrony. Bose-Einstein condensates allow scientists to study quantum phenomena on a scale large enough to observe directly, such as interference patterns and superfluid behavior. They are a powerful tool for exploring fundamental physics, and their existence is a vivid reminder that matter can take on forms utterly unlike the solids, liquids, and gases we encounter in daily life. The creation of Bose-Einstein condensates opened entirely new avenues for studying quantum mechanics and has led to advances in precision measurement and quantum simulation. Fact 61. The quantum Hall effect creates entire new forms of matter. When electrons are trapped in an ultra-thin layer and cooled to near absolute zero in a strong magnetic field, they can exhibit the quantum Hall effect. In this state, electrical resistance takes on precise quantized values, exact fractions or integers that remain stable even if the material has impurities. This effect arises from electrons organizing themselves into new collective quantum states. In some cases, the behavior cannot be explained by ordinary particles at all, but by quasi-particles carrying fractions of an electron's charge. The quantum Hall effect has deepened our understanding of quantum mechanics, topology, and condensed matter physics, and it has potential applications in ultra-precise measurement standards and quantum computing. The discovery revealed that materials can host exotic states of matter, with properties that emerge only from collective quantum behavior, showing that the whole can be radically different from the sum of its parts. Fact 62. Topological materials host states that cannot be destroyed. Topological materials are substances whose electronic properties are determined not just by their composition, but by the shape of their quantum states in abstract mathematical space. One of their most intriguing features is the presence of surface or edge states that are remarkably resistant to disturbance. These states can conduct electricity without scattering even in the presence of impurities or defects. In some cases, they are protected by the material's underlying topology in such a way that they cannot be removed unless the material's fundamental structure changes. These robust properties make topological materials promising for creating stable quantum bits that could resist the noise and errors plaguing today's quantum computers. The topological protection of quantum states represents a new paradigm in condensed matter physics, where geometry and topology rather than just symmetry determine physical properties. Fact 63. Quantum tunneling lets particles pass through solid barriers. In classical physics, if a particle does not have enough energy to climb over a barrier, it simply cannot get through. But in quantum mechanics, there is always a chance it can tunnel right through, appearing on the other side, without ever going over. This happens because particles are described by wave functions that extend into and beyond barriers, giving them a small probability of being found on the far side. Tunneling is crucial in many processes, from nuclear fusion in stars to the operation of tunnel diodes in electronics. It also sets limits on how small we can make certain technologies. In microchips, for example, electrons can tunnel through barriers so thin that they cause unwanted leakage currents. The tunneling phenomenon shows that quantum particles do not respect classical boundaries and can appear in places that should be forbidden by energy considerations, enabling processes that would be impossible in a purely classical world. Fact 64. Stars burn because quantum tunneling makes fusion possible. The sun's core is far cooler than the temperatures you would expect for hydrogen nuclei to overcome their mutual electric repulsion and fuse. Classical physics says fusion should not happen there at all. But quantum tunneling allows nuclei to slip through their mutual repulsion and come close enough for the strong nuclear force to bind them together. This process releases the energy that powers the sun and other stars, and without it the universe would be a much darker place. Tunneling ensures that fusion can occur at the much lower temperatures and pressures found in stellar cores, making it a fundamental enabler of starlight and life. The fact that stars shine at all is a direct consequence of quantum mechanics, showing that quantum effects are not confined to laboratories but operate on cosmic scales throughout the universe. Fact 65. Josephson junctions turn quantum effects into usable circuits. A Josephson junction is made by placing a thin insulating barrier between two superconductors. Quantum tunneling allows paired electrons called Cooper pairs to cross the barrier without any applied voltage, creating a supercurrent. This current can oscillate at incredibly precise frequencies when exposed to a voltage, making Josephson junctions valuable in applications like ultrasensitive magnetometers called squids and voltage standards. They are also central components in many quantum computers where they form the basis of superconducting qubits. Josephson junctions are a clear example of how quantum effects carefully controlled can be turned into practical tools for measurement and computation. The devices demonstrate that quantum phenomena are not just curiosities, but can be engineered into technologies that perform useful functions, bridging the gap between fundamental physics and practical applications. Fact 66. Observing a system constantly can freeze its motion. Known as the quantum Zeno effect, this phenomenon occurs when frequent measurements prevent a quantum system from evolving. In quantum mechanics, measurement collapses a system into a definite state. If you measure it often enough, you can keep resetting it before it has a chance to change, effectively freezing its behavior. This effect has been demonstrated in experiments with atoms and photons, and it has potential applications in controlling quantum states for computing or communication. The quantum Zeno effect turns the idea of observation on its head. Instead of simply revealing reality, observation can shape and even halt it. The phenomenon shows that the act of measurement is not passive but actively influences quantum evolution, and that by timing measurements carefully, we can control quantum systems in ways that have no classical analogue. Fact 67. Quantum levitation lets objects float above magnets. Using superconductors cooled below their critical temperature, it is possible to make objects levitate stably above magnets. This happens because superconductors expel magnetic fields from their interior, the Meissner effect, and can also pin magnetic field lines in place. The result is a locked position in space where the superconductor hovers above or below a magnet, resisting being pushed away or pulled down. Quantum levitation has been used in demonstrations of frictionless motion, and while it is not yet common in everyday transportation, it hints at a future where vehicles could glide without contact powered by quantum effects. The phenomenon provides a visually striking demonstration of macroscopic quantum behavior and has potential applications in energy-efficient transportation systems and ultra-precise positioning mechanisms where friction and wear must be eliminated. Fact 68. Some living things may use quantum tricks to survive. Evidence suggests that certain biological processes may exploit quantum phenomena. In photosynthesis, for example, excitations created by absorbed sunlight seem to travel through plant cells using quantum coherence, taking multiple paths at once to find the most efficient route. Some birds may navigate using quantum entanglement in light-sensitive proteins in their eyes, detecting Earth's magnetic field. Even our sense of smell has been proposed to involve quantum tunneling of electrons in receptor molecules. While these ideas are still under investigation, they suggest that nature may have been harnessing quantum effects long before humans learned to describe them. The possibility that quantum mechanics plays a functional role in biology would blur the boundary between the quantum and classical worlds and show that evolution has discovered ways to exploit quantum phenomena for survival advantages. Fact 69. The early universe was shaped by tiny quantum fluctuations. In the first fractions of a second after the Big Bang, the universe was unimaginably small and hot. A seething quantum field where energy and matter were constantly flickering in and out of existence. Tiny quantum fluctuations in density caused by the uncertainty principle rippled through this early cosmos. These fluctuations were microscopic, but as the universe expanded, they were stretched to cosmic scales. Billions of years later, we can still see their imprint in the faint glow of the cosmic microwave background radiation. They acted as the seeds from which all structure in the universe grew: galaxies, stars, planets, and eventually life itself. Without this quantum noise in the beginning, the universe might have been perfectly smooth and lifeless. The connection between quantum mechanics and cosmology shows that the smallest and largest scales of reality are intimately linked. Fact 70. Those fluctuations grew into all the galaxies we see. Once the early universe cooled enough for gravity to take hold, the slightly denser regions created by quantum fluctuations began to attract more matter. Over millions of years, these regions grew into massive clouds of gas, which eventually collapsed under their own gravity to form the first stars and galaxies. The distribution of galaxies we see today, not random but clustered into vast filaments and walls, traces back to those tiny quantum ripples. In a sense, every galaxy in the night sky is a magnified shadow of a quantum event that happened nearly 14 billion years ago. The fact that quantum fluctuations in the early universe seeded all cosmic structure demonstrates that quantum mechanics is not just relevant at microscopic scales, but has shaped the architecture of the entire observable universe. Fact 71. Black holes follow the rules of quantum mechanics too. We often think of black holes as the domain of Einstein's general relativity, where gravity is king. But black holes also have to obey quantum laws. This becomes especially important at their edges, the event horizon, where intense gravity and quantum fields meet. Effects like Hawking radiation, where black holes slowly emit particles, are purely quantum in nature. Understanding black holes fully requires merging quantum mechanics with gravity, something physicists are still working toward. Studying them could reveal new physics showing how the smallest scale rules of particles connect with the largest scale structure of space-time. Black holes represent natural laboratories where quantum mechanics and general relativity cannot be separated, and understanding them completely may require a theory of quantum gravity that unifies both frameworks. Fact 72. Inflation theory was born from quantum principles. Cosmic inflation is the idea that the universe underwent a brief explosive expansion in its earliest moments, growing far faster than the speed of light. This theory explains why the cosmos appears so uniform on large scales, while still allowing for small variations. Those variations came from quantum fluctuations in the inflaton field itself, stretched across vast distances by the expansion. Without quantum mechanics, inflation would be a very different story, or might not have happened at all. The combination of quantum randomness and rapid growth gave the universe its initial blueprint for all the structure we see today. Inflation connects quantum field theory with cosmology, showing that the same quantum principles operating in particle accelerators also operated during the universe's first moments, shaping everything that would come after. Fact 73. Dark energy could be the energy of the quantum vacuum. In 1998, astronomers discovered that the expansion of the universe is speeding up, driven by something we now call dark energy. One idea is that this mysterious force is just the energy of the quantum vacuum, the background energy that exists even in empty space. Quantum field theory predicts that vacuum energy should exist, but the amount it predicts is vastly larger than what we observe, making this one of the greatest puzzles in physics. If dark energy is truly vacuum energy, then quantum mechanics is not just shaping the tiny world of particles, but steering the fate of the entire cosmos. Resolving the discrepancy between predicted and observed vacuum energy could require new physics and might reveal fundamental limits on what we can know about the universe at the largest scales. Fact 74. Space itself might be made of tiny discrete units. In our daily experience, space feels continuous. You can move any small distance you like. But some theories of quantum gravity suggest that at the Planck scale, space might be made of indivisible grains, the smallest possible units of length. This would be similar to how matter is made of atoms, smooth on large scales but fundamentally discrete underneath. If true, this would mean that space and time are not the basic fabric of reality, but emergent properties built from deeper quantum building blocks. Detecting this granularity directly is beyond current technology, but it may leave subtle fingerprints in the way high-energy particles travel across the universe. The idea that space-time is quantized would resolve certain paradoxes in quantum gravity and provide a natural ultraviolet cutoff that prevents infinities from appearing in calculations. Fact 75. The universe could be one vast quantum object. If everything in the cosmos is connected through quantum entanglement, then in a sense the entire universe might be a single unified quantum system. This idea challenges the classical view of the cosmos as a collection of independent parts. Instead, every particle, field, and force could be part of one vast entangled whole. This concept is speculative, but it fits with hints from cosmology, where correlations between widely separated regions of space seem too precise to have arisen without some deeper connection. If true, the quantum universe might be far more cohesive and far stranger than we imagine. The notion of a universal wave function describing the entire cosmos raises profound questions about what it means for the universe to be observed and whether the cosmos itself could be in a superposition of different states. Fact 76. Quantum gravity aims to unite all of physics. One of the biggest goals in science is to reconcile quantum mechanics with general relativity, the two great theories that currently describe different realms of nature. Quantum gravity seeks to merge them into a single consistent framework that works for both subatomic particles and massive celestial objects. Approaches like string theory, loop quantum gravity, and holography are all contenders, but no final answer has been found. A successful theory of quantum gravity would explain what happens at the center of black holes, what happened at the very beginning of the universe, and perhaps reveal the true nature of space and time. The challenge is immense because quantum mechanics and general relativity use fundamentally different mathematical languages and make different assumptions about the structure of reality. Quantum mechanics treats time as absolute and space as a fixed background, while general relativity shows that space-time itself is dynamic and curved by matter and energy. Finding a way to merge these perspectives is perhaps the greatest unsolved problem in theoretical physics, and its solution could transform our understanding of everything from the smallest particles to the largest cosmic structures. Fact 77. Wormholes might be entanglement made physical. Wormholes, hypothetical tunnels connecting distant points in space-time, have long been a favourite of science fiction. But some physicists propose they could be the geometric manifestation of quantum entanglement. In this idea called ER equals EPR, every entangled pair of particles could be thought of as connected by a tiny non-traversable wormhole. On a cosmic scale, this could mean that space-time structure is built from countless quantum links with wormholes as their visible shape. While still speculative, the concept offers a striking bridge between quantum theory and relativity, suggesting that the fabric of the universe might literally be woven from entanglement. The proposal connects two of Einstein's most famous contributions, the Einstein-Rosen bridge, which describes wormholes, and the Einstein-Podolsky-Rosen paradox, which deals with entanglement. If this connection is real, it would mean that the geometry of space-time and the quantum correlations between particles are two aspects of the same underlying phenomenon. This would provide a concrete mechanism for how entanglement creates spatial connections, and could help resolve paradoxes about information falling into black holes. The idea remains controversial, but it has sparked intense research into the relationship between quantum information and space-time geometry. Fact 78. Quantum physics could be the key to understanding everything. Quantum mechanics already explains the behavior of particles, atoms, and molecules, the foundations of chemistry and biology. It underlies the structure of matter, the flow of energy, and even the evolution of the universe. Yet it also leaves huge mysteries unresolved, from the nature of measurement to the unification with gravity. Some physicists believe that a deep understanding of quantum theory could unlock answers to questions that span all of science, from why the universe exists to whether it could have been different. In this view, quantum physics is not just one part of the puzzle. It may be the puzzle's frame. The quantum world touches everything we know, from the chemical bonds that make life possible to the nuclear reactions that power stars, from the structure of space-time to the origin of cosmic structure. Understanding quantum mechanics more deeply might reveal why the universe has the particular laws and constants it does, why it allows for complexity and structure, and whether other universes with different quantum rules could exist. The centrality of quantum physics to all of science suggests that any truly fundamental theory of reality must be quantum at its core. Fact 79. Reality breaks its own rules at the smaller scales. The familiar rules of physics, the ones that keep planets in orbit and apples falling from trees, start to twist in strange ways when you look at the tinier scales of nature. Down at the level of atoms and subatomic particles, matter can behave like a solid object one moment and a wave the next. Objects can exist in more than one state at a time, and outcomes are dictated by probabilities rather than certainties. Even the act of looking can alter what is being observed. This is not just an odd corner of physics, it is the foundation upon which everything else rests. The fact that reality plays by one set of rules on the surface and an entirely different set underneath is one of the greatest scientific revelations of the past century. The quantum realm operates according to principles that seem to violate common sense, yet these principles are responsible for the stability of atoms, the properties of materials, and the behavior of light. Without quantum mechanics, the world as we experience it could not exist. The periodic table would make no sense, chemical reactions would be impossible to understand, and the sun would not shine. The bizarre rules of the quantum world are not exotic exceptions, but the true foundation of all physical phenomena. Fact 80. Observing a quantum system changes its behavior. In the quantum world, measurement is not passive. When you observe a system, whether it is the position of an electron or the path of a photon, the interaction required to make the observation inevitably changes the system. This is most famously demonstrated in the double-slit experiment, where particles form wave-like interference patterns when left unobserved, but behave like individual particles when measured. The difference is not in the particles themselves, but in the fact that the measurement forces them into a definite state. In quantum mechanics, to look is to touch, and to touch is to change. This has profound implications for what we can know about the quantum world. Every measurement we make disturbs what we are trying to measure in an unavoidable way. This is not a technical limitation that better instruments could overcome, but a fundamental feature of nature. The act of observation involves an exchange of energy or momentum between the measuring device and the system being measured, and this exchange cannot be made arbitrarily small without losing the ability to measure at all. This observer effect shapes how we design experiments and limits what questions we can answer about quantum systems. Fact 81. The Heisenberg uncertainty principle limits what we can know. Werner Heisenberg's uncertainty principle tells us that there are pairs of properties, like position and momentum, that cannot both be known with perfect accuracy at the same time. The more precisely you measure one, the less precisely you can know the other. This is not because our tools are not good enough, but because nature itself does not allow both values to exist exactly at once. The uncertainty principle places a hard limit on knowledge, showing that, at the quantum level, reality is not as sharply defined as it appears. Instead, it exists as a range of possibilities until something narrows them down. The principle applies to other pairs of properties as well, such as energy and time or angular momentum in different directions. It arises from the wave nature of quantum objects and reflects a fundamental property of waves, that they cannot be perfectly localized in both position and momentum simultaneously. The uncertainty principle has practical consequences, limiting the precision of measurements and setting fundamental bounds on what information can be extracted from quantum systems. It also has deep philosophical implications, suggesting that the universe, at its most basic level, is inherently fuzzy, and that perfect knowledge of any system is impossible in principle. Fact 82. Wave functions contain the probabilities of all outcomes. In quantum mechanics, the state of a system is described by its wave function, a mathematical object that encodes all possible outcomes of a measurement and the probabilities of each. The wave function does not tell you exactly what will happen, only the likelihood of each result. Before measurement, the system occupies all of these possible states at once, weighted by probability. When a measurement is made, the wave function appears to collapse into a single outcome. This probabilistic nature is one of the defining features of quantum theory, replacing the clockwork certainty of classical physics with a softer, more flexible reality. The wave function is typically represented as a complex valued function, meaning it has both magnitude and phase. The magnitude squared gives the probability of finding the system in a particular state, while the phase is crucial for determining how different possibilities interfere with each other. The evolution of the wave function over time is governed by the Schrödinger equation, which is completely deterministic, meaning that if you know the wave function at one time, you can predict it at any other time. The randomness enters only when a measurement is made, and the system is forced to choose one outcome from many possibilities. This combination of deterministic evolution and probabilistic outcomes is one of the most puzzling aspects of quantum mechanics. Fact 83. The collapse of a wave function is still a mystery. Physicists can describe wave function collapse mathematically, but they cannot fully explain what physically causes it or whether it even truly happens. In the standard view, the act of measurement forces a quantum system into a definite state. But other interpretations suggest the wave function never collapses and that all possible outcomes happen in parallel worlds. Some collapse models propose that certain processes or scales naturally trigger the collapse without observation. Despite a century of debate, no one has definitively solved this puzzle. The nature of wave function collapse remains one of the most intriguing open questions in physics. The problem is that the Schrödinger equation, which governs quantum evolution, does not contain any mechanism for collapse. The equation is linear and reversible, meaning that if you start with a superposition, you should always have a superposition. Yet experiments clearly show that measurements produce definite outcomes, not superpositions. Various proposals have been made to explain this, including the idea that consciousness causes collapse, that interaction with large systems causes collapse, or that collapse is a spontaneous stochastic process that happens randomly. Each proposal has its strengths and weaknesses, and none has gained universal acceptance. Understanding wave function collapse may require rethinking the foundations of quantum mechanics or discovering new physics beyond the current theory. Fact 84. Quantum systems can exist in multiple states at once. Superposition allows a quantum system to occupy more than one state simultaneously. An electron can be in multiple locations, a photon can take more than one path, and an atom can exist in different energy levels at the same time. This is not just theoretical. It has been confirmed in countless experiments. The trick is that superpositions are delicate collapsing when they interact with their environment. In quantum computers, engineers exploit superposition to perform many calculations in parallel, vastly increasing potential processing power. In nature, superposition is a quiet reminder that reality does not have to choose a single option until it must. The principle of superposition is what makes quantum mechanics quantum. It means that the possible states of a system form a vector space where any combination of basis states is also a valid state. This is fundamentally different from classical physics, where a system must be in one definite state at any given time. Superposition enables quantum interference, where different paths or states can enhance or cancel each other, leading to the characteristic interference patterns seen in quantum experiments. The fragility of superposition is a major challenge for quantum technology, because any interaction with the environment can destroy the quantum coherence needed for quantum computation or communication. Fact 85. Particles can become deeply linked across vast distances. Through the process of entanglement, two or more particles can share a quantum state so completely that measuring one instantly determines the properties of the others no matter how far apart they are. This connection does not fade with distance, and it happens without any known exchange of signals. It is as though the particles are part of the same entity stretched across space. Entanglement is a central feature of quantum mechanics and the basis for emerging technologies like quantum teleportation and quantum cryptography. It is also one of the most mysterious, challenging our classical intuitions about separateness and locality. Entangled particles are described by a single joint wave function that cannot be factored into separate descriptions for each particle. This means that the particles do not have independent properties, but share a single quantum identity. When one particle is measured, the entire entangled system is affected instantaneously, regardless of the spatial separation. This has been verified in experiments over distances of hundreds of kilometers, including tests using satellites in space. Entanglement is now understood to be a resource that can be used for various quantum information tasks, and protecting and manipulating entangled states is a key goal of quantum engineering. Fact 86. Measuring one entangled particle affects the other instantly. In experiments, when scientists measure one particle in an entangled pair, they immediately know the result for the other, even if it is light years away. This effect is instantaneous in terms of correlation, though it does not transmit usable information faster than light. Still, it defies the idea that objects are independent once separated. The particles do not just share similar properties, they share a single quantum description. This spooky action, as Einstein called it, is now a proven aspect of reality confirmed in numerous tests that close possible loopholes. The instantaneous correlation does not violate relativity because no information or energy is transferred between the particles. You cannot use entanglement to send a message faster than light, because the outcome at each location appears random until the results are compared. But the correlations between the measurements are stronger than any classical theory allows, revealing that entangled particles are connected in a way that transcends ordinary space and time. This non-local connection has been tested with increasing rigor over the decades, and every test has confirmed the predictions of quantum mechanics. The phenomenon remains deeply mysterious and continues to challenge our understanding of how reality is structured at the most fundamental level. Fact 87. Quantum correlations cannot be explained by hidden variables alone. Some physicists, including Einstein, once hoped that entanglement could be explained by hidden variables, unseen factors that predetermined outcomes. But experiments inspired by John Bell's theorem have shown that no local hidden variable theory can account for the correlations we observe. Quantum mechanics predicts stronger correlations than any classical theory allows, and nature agrees with quantum predictions. This means the universe is either non-local, allowing influences that transcend distance, or fundamentally different from the tidy deterministic model classical physics envisioned. Bell's theorem provides a mathematical way to distinguish between quantum mechanics and any theory based on local hidden variables. Experiments testing Bell's inequality have consistently violated the inequality in exactly the way quantum mechanics predicts. This rules out the possibility that particles carry hidden information that determines their behavior in advance. The results force us to accept either that measurements on one particle can instantly affect a distant particle, or that particles do not have definite properties until measured. Either option challenges our classical notions of reality and locality, showing that the quantum world operates according to rules that seem impossible from a classical perspective. Fact 88. Some theories suggest entanglement shapes spacetime itself. A provocative idea in modern physics is that spacetime geometry, the distances and connections between points in the universe, might emerge from patterns of quantum entanglement. In this view, the network of entangled particles acts like a scaffolding from which space itself is built. Remove the entanglement, and the geometry could dissolve. This connection between information and geometry is being explored in theories like holography and quantum gravity, hinting that the fabric of reality might be woven not from matter and energy, but from the invisible threads of quantum information. The idea draws on research in string theory and the holographic principle, which suggests that the information content of a region of space is encoded on its boundary. In some models, the amount of entanglement between different regions directly determines the distance between them. Regions that are highly entangled are close together, while regions with little entanglement are far apart. This would mean that space is not fundamental but emergent, arising from the pattern of quantum correlations between underlying degrees of freedom. If this picture is correct, then understanding the structure of entanglement could be the key to understanding the structure of spacetime itself, including phenomena like black holes and the Big Bang. Fact 89. The universe might be a vast web of entanglement. Imagine every particle in the cosmos subtly linked to countless others, forming an invisible network that stretches across all of space. In some theories, this is not just poetic imagery, but literal physics. The universe's structure could be a colossal interconnected web of entanglement. This network would mean that nothing in existence is truly separate. Every atom in your body could in principle be correlated with atoms on the far side of the galaxy. The deeper we study quantum systems, the more it seems that entanglement is not a rare exception, but a fundamental feature of reality itself, possibly shaping the very geometry of space. This universal entanglement would have profound implications for how we understand the cosmos. It would suggest that the separation between objects is an illusion arising from our limited perspective, and that at a deeper level, everything is part of a single unified whole. The cosmic web of entanglement might explain mysterious correlations in the early universe, such as why distant regions of space have nearly identical properties, despite never having been in causal contact. It could also provide a mechanism for how quantum information is preserved during black hole evaporation, solving paradoxes about the fate of information that falls into black holes. Fact 90. Entanglement can be fragile or surprisingly robust. In most cases, entanglement is delicate. The slightest interaction with the environment can break the quantum link, a process called decoherence. This fragility is a major challenge for quantum computing and communication, where maintaining entangled states is essential. Yet under certain conditions, entanglement can persist far longer than expected, even across large distances or in noisy environments. Some materials naturally protect entanglement, and certain protocols can purify and strengthen it. Understanding how to preserve these fragile connections could be the key to building reliable quantum technologies and exploring the role of entanglement in nature. Researchers have discovered that certain types of entanglement are more robust than others. For example, entanglement between multiple particles can sometimes be protected by collective effects that make it harder for the environment to destroy the quantum correlations. Topological states of matter can harbour entanglement that is protected by the material's geometric properties, making it resistant to local perturbations. Quantum error correction codes have been developed that can detect and fix errors that would otherwise destroy entanglement, allowing quantum information to be preserved even in the presence of noise. These advances bring practical quantum technology closer to reality and deepen our understanding of how quantum coherence can survive in the complex, messy world outside carefully controlled laboratory environments. Fact 91. Virtual particles flicker in and out of existence. Even in the vacuum of space where no real particles exist, quantum fields are never completely still. Energy fluctuations constantly create pairs of virtual particles and antiparticles which appear briefly before annihilating each other. These fleeting visitors can have real effects. They contribute to forces between particles, shift the energy levels of atoms, and even affect the behavior of black holes. While virtual particles cannot be directly observed, their fingerprints are found in precise experiments, showing that empty space is far from empty. Virtual particles are a consequence of the uncertainty principle, which allows energy to fluctuate by an amount inversely proportional to the timescale of the fluctuation. The shorter the time, the larger the energy fluctuation that can occur. These fluctuations manifest as temporary particle-antiparticle pairs that pop into existence, borrow energy from the vacuum, and then annihilate, returning the energy. Although virtual particles exist only briefly, they have measurable effects. They contribute to the Lamb shift in hydrogen, alter the magnetic moment of the electron, and produce the Casimir force between conducting plates. In quantum field theory, virtual particles mediate all fundamental forces, with photons carrying the electromagnetic force, gluons carrying the strong force, and W and Z bosons carrying the weak force. Fact 92. Hawking radiation emerges from quantum vacuum effects. Stephen Hawking's groundbreaking work showed that black holes are not perfectly black. At their event horizons, quantum fluctuations can cause one particle of a virtual pair to fall in, while the other escapes, becoming real. This slow leakage of energy, known as Hawking radiation, means black holes can eventually evaporate over immense timescales. It is a rare meeting point between quantum mechanics and gravity, and it raises deep questions about what happens to information that falls into a black hole, a mystery still hotly debated today. The temperature of Hawking radiation is inversely proportional to the black hole's mass, meaning that larger black holes are colder and evaporate more slowly, while smaller black holes are hotter and evaporate faster. For a stellar mass black hole, the Hawking temperature is far below the cosmic microwave background, so these black holes are actually absorbing more energy than they emit. But in the distant future, when the universe has cooled, even stellar mass black holes will begin to evaporate, and over incredibly long time scales, all black holes will eventually disappear in a final burst of radiation. The process raises profound questions about information conservation, because if black holes can destroy information, it would violate fundamental principles of quantum mechanics. Fact 93. Vacuum energy may drive cosmic expansion. The vacuum of space holds a tiny amount of residual energy, and according to Einstein's equations, energy has gravity. If the vacuum has energy, it should cause a repulsive effect, pushing space apart. This could explain dark energy, the mysterious force causing the universe's accelerated expansion. The puzzle is that quantum field theory predicts a vacuum energy vastly larger than what we observe. Reconciling this mismatch is one of the biggest open problems in physics. Solving it might reveal new insights into both cosmology and quantum theory. The discrepancy between the predicted and observed vacuum energy is enormous, about 120 orders of magnitude, making it the worst prediction in the history of physics. This suggests that something fundamental is missing from our understanding either about how to calculate vacuum energy or about how it affects the universe. Some physicists speculate that there might be a mechanism that cancels most of the vacuum energy, leaving only a tiny residual amount. Others suggest that the vacuum energy we observe might not be quantum vacuum energy at all, but something else entirely, perhaps related to a dynamical field that evolves over cosmic time. Fact 94. The nature of the vacuum remains a profound mystery. We can describe the quantum vacuum, mathematically measure its effects in experiments, and even connect it to cosmic scale phenomena. But we still do not truly understand what it is. Is it a physical medium like an invisible ocean filling space? Is it a property of fields that exist whether or not particles are present? Or is it something even stranger, perhaps tied to the origin of the universe itself? The vacuum sits at the intersection of quantum theory, relativity, and cosmology, three pillars of physics that still resist full unification. Until we understand it completely, the emptiness between the stars will remain one of the most profound and mysterious aspects of reality. The quantum vacuum may hold clues to some of the deepest questions in physics, including why the universe exists, why it has the properties it does, and whether it could have been different. Some theories suggest that the vacuum is not in its lowest energy state, but in a metastable state that could decay to a lower energy, releasing enormous amounts of energy in the process. This raises the unsettling possibility that the vacuum could undergo a phase transition, sweeping through space at the speed of light and fundamentally altering the laws of physics in its wake. Fact 95. Quantum computers can think in many realities at once. Unlike classical computers which process information in binary bits that are either 0 or 1, quantum computers use qubits, units that can exist in superpositions of 0 and 1 at the same time. This allows them to explore many possible solutions simultaneously, as if they are testing outcomes across multiple realities before settling on an answer. The power of this approach grows exponentially with the number of qubits making certain problems that would take classical computers millennia potentially solvable in seconds. Quantum computers are still in their infancy, struggling with error correction and stability, but even now they hint at a future where problems in chemistry, cryptography, and optimization could be cracked with breathtaking speed. It is not magic. It is the quantum rules of probability and interference harnessed in a way that classical logic could never match. The challenge is that qubits are extremely fragile, and maintaining their quantum state long enough to perform useful computations requires isolating them from environmental noise, cooling them to temperatures near absolute zero, and implementing sophisticated error correction protocols. Despite these challenges, quantum computers have already demonstrated quantum supremacy, performing certain tasks faster than any classical computer could, and the field is advancing rapidly with both academic researchers and major technology companies investing heavily in quantum computing development. Fact 96. Qubits can store multiple answers in a single moment. A qubit is not locked into a single state until it is measured. Before then, it can hold a blend of possibilities, both 0 and 1 weighted by probabilities. This property is what gives quantum computers their massive potential power. With just a handful of qubits, you can represent an astronomical number of possible combinations at once. When a quantum algorithm runs, it manipulates these probabilities in a carefully choreographed way, so that the wrong answers cancel each other out, and the correct one remains. It is like searching an entire library in parallel instead of book by book. The catch is that measurement collapses a qubit state, so designing algorithms that extract useful results from this delicate superposition is one of the central challenges in quantum computing. The key to quantum computing is quantum interference, where different computational paths can interfere constructively or destructively. A well-designed quantum algorithm arranges things so that paths leading to wrong answers interfere destructively and cancel out, while paths leading to correct answers interfere constructively and are amplified. This requires careful control of both the magnitude and phase of the quantum amplitudes, which is why quantum algorithms are often quite different from their classical counterparts, and why only certain types of problems benefit from quantum speedup. Fact 97. Entanglement supercharges quantum processing. Entanglement is not just a curiosity, it is a resource. In quantum computing, entangled qubits share correlations that classical bits never could, allowing operations on one qubit to instantly influence its entangled partners. This enables quantum computers to perform complex computations more efficiently, linking distant parts of a problem together without moving physical information around. Entanglement also plays a role in error correction, helping detect and fix mistakes without directly observing the qubit's fragile states. Without entanglement, quantum computers would lose much of their advantage over classical machines. It is the invisible thread that ties their logic together, giving them the power to tackle problems far beyond the reach of today's fastest supercomputers. Creating and maintaining entanglement between qubits is one of the primary engineering challenges in building quantum computers. Qubits must be coupled strongly enough to become entangled, but isolated well enough from the environment to prevent decoherence. Different physical implementations of qubits, such as superconducting circuits, trapped ions, or photons, have different strengths and weaknesses when it comes to generating and preserving entanglement. Quantum error correction codes rely on entanglement to spread quantum information across multiple physical qubits, creating logical qubits that are more resistant to errors. The development of large-scale entanglement between many qubits is essential for building practical quantum computers that can solve real-world problems. Fact 98. Certain quantum algorithms could solve problems instantly. Some quantum algorithms are so efficient that they could in principle crack problems that would stump classical computers for centuries. One famous example is Shor's algorithm, which can factor large numbers exponentially faster than the best-known classical methods, a breakthrough that could undermine many of today's encryption systems. Another is Grover's algorithm, which can speed up database searches in a way no classical approach can match. These algorithms do not make quantum computers universally faster, but for the problems they are suited to, the advantage can be enormous. This is why governments, tech companies, and researchers are racing to develop practical quantum processors. The first to do so will unlock computational capabilities that could reshape technology and security. Shor's algorithm works by exploiting the quantum Fourier transform to find the period of a function, which can be used to factor numbers efficiently. This poses a serious threat to RSA encryption, which relies on the difficulty of factoring large numbers for security. In response, cryptographers are developing post-quantum cryptography algorithms that would remain secure even against quantum computers. Grover's algorithm provides a quadratic speedup for unstructured search problems, which is less dramatic than the exponential speedup of Shor's algorithm, but still significant for certain applications. Beyond these well-known algorithms, researchers continue to discover new quantum algorithms for problems ranging from simulating quantum systems to optimizing logistics and machine learning. The implications of quantum algorithms extend far beyond cryptography. In chemistry, quantum computers could simulate molecular interactions with precision impossible for classical computers, allowing researchers to design new drugs and materials by exploring the quantum behavior of electrons in complex molecules. In optimization, quantum algorithms could find better solutions to problems like route planning, resource allocation, and financial portfolio management, where the number of possible solutions grows exponentially with problem size. In machine learning, quantum algorithms could potentially speed up training of neural networks and enable new forms of pattern recognition by exploiting quantum interference and entanglement. The field of quantum algorithms is still young, and many researchers believe we have only scratched the surface of what quantum computers can do. As we develop a deeper understanding of quantum information and quantum complexity theory, we may discover entirely new classes of problems where quantum computers provide dramatic advantages. However, it is also becoming clear that quantum computers will not replace classical computers, but rather complement them with each type of computer suited to different kinds of tasks. The challenge for algorithm designers is to identify which problems can benefit from quantum speedup, and to develop practical quantum algorithms that can run on the noisy intermediate-scale quantum devices available today, while working toward the fault-tolerant quantum computers of the future. Fact 19. Quantum cryptography creates secrets that cannot be cracked. Classical cryptography relies on the difficulty of certain mathematical problems, but in theory a powerful enough computer could break them. Quantum cryptography, by contrast, uses the laws of physics to guarantee security. The most famous method, quantum key, distribution sends encryption keys encoded in the states of photons. Any attempt to eavesdrop inevitably disturbs these states, revealing the intrusion instantly. This means that secure communication is possible even over channels an attacker can fully observe. Quantum cryptography has already been tested in real-world networks, including satellite links, and could one day protect financial transactions, government communications, and personal data with a level of security no classical system can match. The security of quantum key distribution does not depend on computational assumptions, but on the fundamental laws of quantum mechanics, particularly the no-cloning theorem, which states that arbitrary quantum states cannot be copied perfectly. This means that an eavesdropper cannot intercept quantum encrypted messages without leaving detectable traces. Several quantum key distribution protocols have been developed with different trade-offs between security, efficiency, and practicality. The technology has matured to the point where commercial quantum cryptography systems are available, and quantum encrypted communication networks are being deployed in several countries. As quantum computers advance and threaten classical encryption, quantum cryptography may become essential infrastructure for secure communication in the quantum age. The most widely used protocol, BB84, named after its inventors Bennett and Broussard, and the year 1984, works by encoding information in the polarization states of photons. The sender prepares photons in one of 4 possible polarization states, and the receiver measures them using randomly chosen measurement bases. After transmission, the sender and receiver compare their choices of bases over a public channel without revealing the actual measurement results. They keep only the results where they happen to use matching bases, which become the secret key. If an eavesdropper tried to intercept the photons, they would have to measure them, disturbing their quantum states, and introducing errors that the legitimate parties can detect by comparing a subset of their key. The beauty of this approach is that the laws of quantum mechanics guarantee security no matter how powerful the eavesdropper's technology becomes. Quantum key distribution has been demonstrated over optical fibers spanning hundreds of kilometers, and even between ground stations and satellites in space, opening the possibility of global quantum encrypted communication networks. China has already deployed a quantum communication satellite and built a quantum encrypted network connecting several cities. Banks and government agencies are beginning to adopt quantum cryptography to protect their most sensitive communications. The main challenges facing quantum cryptography are extending the range of quantum key distribution, developing quantum repeaters that can extend quantum networks over longer distances, and integrating quantum security with existing communication infrastructure. Researchers are also exploring other quantum cryptographic protocols beyond key distribution, including quantum digital signatures and quantum secure direct communication, each offering unique security advantages based on quantum principles. Fact 100. Quantum sensors detect the barest whispers of change. By exploiting quantum effects like superposition and entanglement, quantum sensors can measure quantities such as time, acceleration, and magnetic fields with extraordinary precision. They are so sensitive that they can detect changes too small for any classical instrument, shifts caused by tiny gravitational variations, subtle brain activity, or even the presence of dark matter particles. Some designs use clouds of ultra-cold atoms or nitrogen vacancy centers in diamond to achieve this sensitivity. In the future, quantum sensors could revolutionize navigation, medical imaging, and geological surveying, opening new windows into both the human body and the Earth itself. Quantum sensors work by putting quantum systems into carefully prepared states that are exquisitely sensitive to the quantity being measured. For example, atomic clocks use the precise frequency of atomic transitions. Quantum gravimeters use the interference of matter waves to measure acceleration, and quantum magnetometers use the spin states of atoms or defects in solids to detect magnetic fields. These sensors can achieve sensitivities that approach fundamental quantum limits, making them far more precise than classical sensors. Applications range from detecting submarines by their magnetic signatures to mapping underground mineral deposits to monitoring brain activity with unprecedented resolution. As quantum sensor technology continues to advance, it promises to open entirely new ways of probing the world around us, revealing phenomena that were previously invisible to our instruments, and expanding the frontiers of science, medicine, and exploration. The principle behind quantum sensors is that quantum systems can be placed in superpositions that make them extremely sensitive to external influences. When a quantum sensor is in a superposition of two states, any external field or force that affects those states differently will cause the superposition to evolve in a measurable way. By carefully preparing the initial state and precisely measuring the final state, after some time, scientists can detect incredibly small perturbations. Atomic interferometers, for instance, split atom clouds into superpositions where each atom travels along two different paths simultaneously. Any difference in the environment along these paths, such as a gravitational field gradient, causes the paths to accumulate different quantum phases. When the paths are recombined, the atoms interfere, and the interference pattern reveals information about the field. These devices can measure gravity with such precision that they can detect changes in underground water levels or the presence of buried structures. Nitrogen vacancy centers are defects in diamond where a nitrogen atom replaces a carbon atom and an adjacent lattice site is empty. These defects have quantum properties that make them sensitive to magnetic fields' temperature and electric fields. They can be used at room temperature, making them practical for many applications. Researchers have used them to image magnetic fields produced by neurons, firing in the brain to study the magnetic properties of materials at the nanoscale, and even to search for exotic physics beyond the standard model. Quantum sensors are also being developed for gravitational wave detection, where they could complement existing observatories by accessing different frequency ranges. In navigation, quantum accelerometers and gyroscopes could provide positioning information without relying on GPS satellites, which can be jammed or unavailable in certain environments. In medical imaging, quantum sensors could enable new forms of brain scanning that reveal neural activity with much higher spatial and temporal resolution than current methods. The potential applications of quantum sensing are vast, and as the technology matures, it will likely transform numerous fields by providing access to information that was previously beyond our reach, giving us new tools to explore the quantum world and the classical world with unprecedented precision.